Turn off the lights, my friend. I am HyperSleep Logs. Together, we're stepping into the deep mysteries of the cosmos. Our journey begins, right now, the day we met the stranger, understanding Oumuamua and what it means for humanity. Listen, I need to tell you about something that happened in October 2017 that completely changed the way we think about our place in the universe. And I'm not being dramatic here. This is one of those moments in human history where we crossed a threshold we can't uncross. We saw something that came from somewhere else. And we're still trying to figure out what the hell it was. So let me take you back to that night in Hawaii. Picture the massive telescope on Haleakala, scanning the sky like it does every clear night, looking for asteroids that might threaten Earth. It's routine work, honestly. Most nights, you find rocks, space debris, the usual suspects that have been orbiting our sun since the solar system formed about 4.5 billion years ago. But on this particular night, the telescope caught something moving. Just a faint pixel, really. Moving fast. Really fast. At first, nobody thought much of it. Probably just another asteroid, right? But then the astronomers started doing the math, and that's when things got weird. This object, later designated 1I/2017 U1 and eventually nicknamed Oumuamua, which means scout or messenger in Hawaiian, wasn't following the rules. Its trajectory was all wrong. It was moving at about 26 kilometers per second relative to the sun, which is insanely fast. But more importantly, the shape of its path through our solar system told a story that made everyone's hair stand on end. It came from outside. Not from the Kuiper Belt, where Pluto hangs out. Not from the Oort cloud, that distant shell of icy bodies at the edge of our solar system. No, this thing came from interstellar space. From between the stars. From the deep, cold void where nothing should be traveling except maybe a few stray hydrogen atoms and the occasional cosmic ray. Think about what that means for a second. This object had been traveling through absolute darkness for hundreds of millions of years. We're talking about a journey that began when dinosaurs still walked the Earth, or maybe even earlier. It had survived temperatures just barely above absolute zero, -270 degrees Celsius, if you want to get specific. It had endured radiation that would sterilize anything we could imagine. And it had somehow held together through all of that, tumbling end over end through the loneliest reaches of space, until it happened to pass through our tiny corner of the galaxy at exactly the moment when we had finally developed telescopes good enough to see it. If Oumuamua had arrived just 20 years earlier, we would have missed it completely. It would have sailed right through our solar system like a ghost, and we'd still be sitting here thinking we were alone, that nothing from out there ever visits. But we did see it. And what we saw was, well, let me put it this way, it was weird. Really, really weird. The first hint that something was off came from watching how its brightness changed. See, when an object tumbles through space, the amount of sunlight it reflects changes depending on which side is facing us. By carefully measuring these brightness variations, astronomers can figure out an object's shape. And Oumuamua's shape was bonkers. The brightness changed by a factor of 10 as it rotated, which meant this thing had to be at least 10 times longer than it was wide. Imagine a cigar. Or better yet, imagine a needle. A cosmic needle, somewhere between 100 and 400 meters long, but maybe only 40 meters wide. Now, here's the thing, we've never seen anything like that in nature. Not in our solar system, anyway. Asteroids are usually lumpy, potato-shaped things. Comets are irregular chunks of ice and rock. But a needle, a sliver, that's not normal. That's not how gravity likes to shape things when they form. When rocks collide and accrete in space, they tend to make roundish blobs, not elongated needles. The forces involved just don't work that way. But okay, maybe it's just a weird natural formation. Maybe there's some process we don't understand yet that can create needle-shaped rocks. The universe is full of surprises, right? So the scientific community was willing to accept this oddity. Unusual, sure, but not impossible. Then it did something that should have been impossible. As Oumuamua swung around the sun and began heading back out into interstellar space, astronomers noticed it was accelerating. Not just moving at a constant speed, actually speeding up. And that tiny acceleration, subtle as it was, broke everything we thought we knew about how these objects should behave. See, when a comet gets close to the sun, it heats up. Ice on its surface turns directly into gas, a process called sublimation, and that gas jets off into space. These jets act like tiny rocket engines, giving the comet a little push. This is completely normal. We've seen it hundreds of times. It's called outgassing, and it's why comets have those beautiful tails. But here's the catch: when a comet outgasses, we can see it. We can detect the gas and dust streaming off its surface with our telescopes. We can measure the composition of that gas. We can photograph the tail. It's obvious and unmistakable. Oumuamua. Nothing. Absolutely nothing. The scientists pointed every instrument they had at it. The Spitzer Space Telescope, which can detect the faintest infrared signals, stared at Oumuamua looking for any sign of gas or dust. They looked for water vapor, carbon dioxide, carbon monoxide, all the usual suspects. They looked for dust particles reflecting sunlight. They looked for anything that would explain that acceleration. They found zilch. Nada. The object was completely clean. No tail. No coma, that fuzzy cloud of gas that surrounds an active comet. No visible outgassing whatsoever. And yet, it was speeding up, being pushed by some invisible force that gravity alone couldn't account for. This is where things get really interesting, and where the scientific community basically split into camps. Because if you accept the data, and the data was solid, you're left with a problem that has no easy answer. The traditionalists, the scientists who wanted to keep Oumuamua in the category of natural object, started proposing increasingly creative explanations. The first major theory was the hydrogen iceberg hypothesis. The idea goes like this: what if Oumuamua was made of solid molecular hydrogen? If hydrogen ice sublimates, it's invisible to our telescopes. We wouldn't see a tail or detect any gas, but it would still provide thrust, giving the object that mysterious acceleration. Problem solved, right? Well, not exactly. Here's the issue with the hydrogen iceberg idea: hydrogen ice is incredibly fragile. We're talking about something that starts to evaporate at temperatures barely above absolute zero. And here's the thing: interstellar space isn't actually at absolute zero. There's ambient starlight from all the stars in the galaxy. It's faint, sure, but it's there, and it heats things up, even if only by a few degrees. A chunk of hydrogen ice traveling through the galaxy for hundreds of millions of years would have been slowly evaporating the entire time, long before it ever got close to our sun. By the time it reached us, there'd be nothing left. The math just doesn't work out. So then came the nitrogen fragment theory. This one's a bit more plausible. The idea is that Oumuamua is a chunk of frozen nitrogen that was blasted off a Pluto-like planet in another star system during some catastrophic collision. Nitrogen ice is more stable than hydrogen. It could potentially survive the journey. And like hydrogen, it could sublimate invisibly, providing that mysterious thrust without leaving a visible tail. But here's where this theory runs into trouble. If nitrogen fragments like Oumuamua are common enough that we spotted one just a few years after we developed the technology to detect them, then the galaxy must be absolutely littered with these things. We're talking about an enormous number of fragments. And that would mean that Pluto-like planets in other star systems are getting smashed to pieces at a rate that's way higher than anything we'd expect based on what we know about planetary formation and collision rates. It's possible, but it requires a whole lot of special pleading and some pretty unlikely coincidences. And that's when some scientists started looking at the third possibility. The one that makes everyone uncomfortable. If Oumuamua wasn't outgassing, then the only other force that could push an object like this is light itself. Sunlight. Radiation pressure. Now, radiation pressure is real. Light carries momentum, and when photons bounce off an object, they give it a tiny push. We've known this for over a century. It's the principle behind solar sails, which some space agencies are actually developing for future missions. But here's the thing. For sunlight to push a macroscopic object enough to produce the acceleration we observed, that object has to have a very specific relationship between its surface area and its mass. It has to be incredibly thin and incredibly light. When you run the numbers for Oumuamua, you get a mass-to-area ratio of about 0.1 grams per square centimeter. Let me put that in perspective for you. A standard sheet of office paper has a mass-to-area ratio that's about 800 times higher than that. We're talking about something thinner than aluminum foil. Thinner than a soap bubble. We're talking about a membrane. And here's where we hit the uncomfortable question. Does nature make membranes that are hundreds of meters long and strong enough to survive the interstellar medium for millions of years? No. Nature doesn't make those. Engineering does. This is the hypothesis that Professor Avi Loeb from Harvard put forward, and it caused an absolute firestorm in the scientific community. Loeb argued, quite reasonably, that if we've eliminated all the natural explanations and they don't fit the data, we should at least consider the possibility that Oumuamua is artificial. Not necessarily an active probe, but maybe a piece of technology. A defunct solar sail. A fragment of something larger. Space junk from another civilization. The backlash was immediate and intense. A lot of scientists were furious. They accused Loeb of sensationalism, of jumping to conclusions, of violating the fundamental principle that extraordinary claims require extraordinary evidence. And look, I get it. The idea that we've been visited by alien technology is pretty extraordinary. It's the kind of thing that can make you sound like a crackpot if you're not careful. But here's what I find fascinating about this whole debate. In their rush to avoid the alien technology hypothesis, some scientists were willing to invent new physics, new types of materials that we've never seen, and new processes that violate what we know about chemistry and thermodynamics. They were willing to accept extraordinarily unlikely natural explanations rather than even consider the possibility of artificial origin. Loeb pushed back on this, famously saying, "Extraordinary conservatism leads to extraordinary ignorance." And you know what? He's got a point. If we refuse to follow the data just because it leads us somewhere uncomfortable, we're not doing science anymore. We're doing philosophy. Or worse, we're doing dogma. So let me lay out the evidence as clearly as I can, and you can decide for yourself what makes more sense. Oumuamua is shaped like a needle or a disc, something with an extreme aspect ratio that we've never seen in a natural object. It accelerated away from the sun without any visible outgassing. It tumbled in a stable way that suggests it's a single, solid object rather than a loose pile of rubble. Its surface was covered in a reddish organic coating consistent with millions of years of radiation exposure in deep space. And perhaps most tellingly, it was moving at the local standard of rest. That last point deserves some explanation, because it's actually really important. The local standard of rest, or LSR, is basically the average velocity of stars in our neighborhood of the galaxy. Most stars, including our Sun, are moving relative to the LSR. We're all orbiting the galactic center at different speeds and angles. But Oumuamua was just sitting still relative to the LSR. It was like a buoy floating in the ocean while our solar system was the speedboat that happened to zoom past it. This is significant for two reasons. First, only about 1 in 500 stars in our region is at rest relative to the LSR. For a random object to be in that state is statistically really unlikely. Second, if you were an advanced civilization and you wanted to monitor a large volume of space with the least amount of energy expenditure, what would you do? You wouldn't send active probes to chase down every star. That would take too much fuel. No, you put your monitors at rest in the LSR and just wait for the stars to come to you. It's elegant. It's efficient. And it's exactly what we saw. Now, I'm not saying Oumuamua is definitely a probe. I'm saying the data we have is consistent with it being artificial, and we shouldn't dismiss that possibility just because it makes us uncomfortable. Let me tell you about the color, because this is another piece of the puzzle. Oumuamua was red. Not just a little red, dark red, like the surface of Pluto. This color comes from organic compounds called tholins, which form when simple hydrocarbons are bombarded by ultraviolet radiation for millions of years. We see these same compounds on the surfaces of objects in the outer solar system, so in that sense, Oumuamua's color is perfectly normal. But think about what that color means. It means this object has been exposed to the harsh radiation environment of interstellar space for an incredibly long time. The tholins are like a weathered crust, protecting whatever lies underneath. And here's the interesting part: if Oumuamua is artificial, that crust might be acting as camouflage. After millions of years in space, even a manufactured object would accumulate this natural-looking coating. At first glance, it would appear to be just another reddish asteroid. It's only when you look at how it moves, how it accelerates, that the mask slips. The question that keeps me up at night is this: if Oumuamua is a piece of technology, where did it come from? When we trace its trajectory backward, it doesn't point to any nearby star system. It came from the direction of Vega, but Vega wasn't in that position when Oumuamua would have left its origin point. The object is old. Really old. It's been traveling for so long that whatever star it came from has moved, and we can't figure out where it originated. This leads to some unsettling possibilities. Maybe Oumuamua comes from a star system that's so far away we'll never identify it. Maybe it comes from a system whose star has already died. Or maybe, and this is the really wild possibility, it's not from any star system at all. Maybe it's part of some larger infrastructure. A monitoring network. A galactic positioning system. Something left behind by a civilization that operated on scales we can barely imagine. There's a theory, speculative but fascinating, that Oumuamua could be a fragment of a Dyson sphere. You know what a Dyson sphere is, right? It's a hypothetical megastructure that an advanced civilization might build around their star to capture all of its energy output. The sphere would be made of countless panels or shells, all designed to absorb starlight. Now, over millions or billions of years, some of those panels would inevitably get knocked loose by asteroid impacts or other cosmic events. They'd be ejected into interstellar space, and they'd drift. These panels would be thin, designed to maximize surface area while minimizing mass. They'd be made of materials engineered to withstand radiation. And if they sublimated material designed to be invisible to our telescopes, they'd accelerate without leaving a visible trail. Sound familiar? I'm not saying Oumuamua is definitely a piece of a Dyson sphere. But it's worth noting that if such objects exist, Oumuamua is exactly what we'd expect them to look like. Now, let's talk about what happened after we discovered this thing, because the story gets even more interesting. As soon as scientists realized Oumuamua was leaving the solar system, and leaving fast, there was a scramble to learn everything possible before it disappeared forever. Teams around the world pointed their telescopes at it. They measured its rotation rate, about 8 hours per tumble. They analyzed its brightness. They looked for any radio signals or other signs of activity. They studied its trajectory with extreme precision. And you know what they found? Nothing that answered the big questions. Just more puzzles. The object was tumbling chaotically, which suggested it wasn't under active control. If it was a functioning probe, you'd expect it to be stabilized, oriented properly for whatever its mission was. But Oumuamua was spinning like a football thrown by a kid who doesn't know how to throw a spiral. This tumbling motion actually supports the idea that it's a derelict object. A piece of space junk. Something that was functional once but has long since broken down. Think about it this way, if Oumuamua is artificial, it's probably older than human civilization. It could be older than multicellular life on Earth. It's been drifting through the galaxy for longer than we can really comprehend, and any systems it once had, power supplies, stabilizers, communication equipment, would have failed eons ago. We're not looking at a working machine. We're looking at a fossil. A technofossil, as some researchers have started calling it. This idea, that the galaxy might be littered with the remains of extinct civilizations, is both fascinating and deeply melancholy. It suggests that intelligence in the universe might be common, but also transient. Civilizations rise, they build amazing things, they spread out into space, and then, something happens. They decline. They die out. Maybe they destroy themselves. Maybe they just fade away. But their artifacts remain, drifting through the void long after their creators are gone. This brings us to what's called the Great Filter Hypothesis. The idea is that there's some barrier, some extremely difficult challenge, that prevents civilizations from expanding and lasting for very long. Maybe it's nuclear war. Maybe it's climate change. Maybe it's artificial intelligence gone wrong. Maybe it's something we haven't even thought of yet. But whatever it is, it seems to stop civilizations before they can colonize the galaxy. If Oumuamua is artificial, it might be evidence of a civilization that passed through the Great Filter and didn't make it. Their last remnants are these silent monuments, tumbling through space, visiting solar systems long after anyone is left to receive the data they collect. That's a sobering thought. It suggests that even if life and intelligence are common in the universe, we might still be effectively alone, surrounded by ruins rather than neighbors. But there's another interpretation, one that's slightly more hopeful. Maybe civilizations do last, but they operate on such different timescales or in such different ways that we simply don't recognize them. Maybe they've moved beyond physical form. Maybe they don't build radio transmitters because they've found better ways to communicate. Maybe they don't care about biological planets like Earth because they've adapted to live in space or in virtual realities. Maybe Oumuamua is just a piece of infrastructure from a civilization that's still out there, doing their thing, completely uninterested in a primitive species like us that's just barely started to explore its own solar system. I don't know which interpretation I find more unsettling, honestly. Now, here's where the story takes a frustrating turn. By the time we'd figured out how weird Oumuamua was, it was already too far away to do anything about it. The object was moving at such high speed that catching up to it with our current technology would be nearly impossible. We watched it disappear back into the darkness, carrying all its secrets with it, and there was nothing we could do. Except, maybe there is. Enter Project Lyra. This is a mission concept that's been in development since Oumuamua's discovery. The idea is to use a maneuver called a solar oberth to catch up to the object before it gets too far away. Here's how it works. You build a spacecraft and launch it toward the sun. As it gets closer and closer to the sun, falling down into that enormous gravity well, it picks up speed. Then, at the moment of closest approach, when the spacecraft is screaming through the sun's corona at tens of kilometers per second, you fire the engines. Because you're already moving so fast, the thrust from the engines is amplified, giving you a massive velocity boost. With this maneuver, you could potentially accelerate a spacecraft to speeds high enough to catch Oumuamua in the outer solar system or even in interstellar space beyond. It's an audacious plan. The spacecraft would need heat shields capable of surviving temperatures hot enough to melt most metals. It would need autonomous navigation systems, because at those distances, radio signals take hours to reach Earth and back. You can't fly it remotely. It would need to carry instruments capable of analyzing Oumuamua in detail, cameras for close-up photography, spectrometers to analyze the surface composition, maybe even a radar or laser to probe the interior structure. And here's the beauty. Full irony, to catch Oumuamua, we'd probably need to use the same technology it might represent. We'd need to build our own solar sail. We'd use light pressure from the sun or from giant lasers to accelerate a thin, lightweight probe to a significant fraction of light speed. Technology chasing technology across the abyss. If we pull this off, if we actually manage to rendezvous with Oumuamua and get a close look at it, it would be one of the most important moments in human history. Even if it turns out to be just a weird rock, we'd learn something profound about how objects form in other star systems. We'd get data on interstellar material composition, on radiation effects, on 1,000 things we can only guess at right now. But if it turns out to be artificial, God, I can't even imagine what that would mean. We'd have physical proof that we're not alone. We'd have evidence that other civilizations have developed technology, that they've built things, that they've sent those things out into the galaxy. We'd know, with absolute certainty, that intelligence has arisen elsewhere in the universe. And even if that particular civilization is long gone, it would fundamentally change our understanding of our place in the cosmos. Think about what we might find if we got up close. Maybe we'd see a metallic surface, pitted and scarred by billions of micrometeorite impacts. Maybe we'd see regular patterns, structural ribs, evidence of manufacturing. Maybe we'd find symbols or markings that would tell us something about whoever built it. Or maybe we'd find that it's just a chunk of weird nitrogen ice after all, and we'd have to accept that nature is even stranger than we thought. Either way, we'd know. And knowing is worth the effort, worth the cost, worth the risk. But here's the thing that really gets me. Every day we wait, Oumuamua gets farther away. Every month that passes without launching a mission is a month where the object recedes deeper into space, becoming harder and harder to catch. There's a window here, and that window is closing. If we don't act soon, we'll lose our chance. Oumuamua will disappear into the interstellar void, and we'll be left with nothing but blurry images and unanswered questions. Some people argue that we shouldn't worry about Oumuamua because we'll see more objects like it. And they're probably right. Astronomers estimate that there are probably thousands of interstellar objects in our solar system at any given time, most of them too small or too dark for us to detect with current technology. But we're about to get a lot better at finding them. The Vera C. Rubin Observatory, which is coming online soon, is going to revolutionize our ability to detect these visitors. This telescope will survey the entire visible sky every few nights, looking for anything that moves. It's going to find asteroids, comets, and, almost certainly, more interstellar objects. Based on current estimates, the Rubin Observatory might detect one interstellar visitor every month. Maybe one every week. And that's when things are really going to get interesting. Because if we find more objects like Oumuamua, and they all show the same weird characteristics, the same acceleration, the same lack of outgassing, the same extreme shapes, then the natural explanation is going to become increasingly hard to defend. If we see a pattern, if we see a population of these things all behaving the same way, we're going to have to seriously consider the possibility that we're looking at artifacts. That the space between stars is not empty, but is actually filled with the remnants of countless civilizations. This would completely transform our search for extraterrestrial intelligence. For decades, we've been listening for radio signals, assuming that if aliens exist, they'll communicate the way we do. We've been looking for deliberate messages, for someone trying to say hello. But Oumuamua suggests we should be looking for the physical evidence of their presence. Their archaeological remains. Their trash. Their ruins. This field is starting to be called astroarchaeology or galactic archaeology, and it's a fascinating shift in perspective. Instead of listening, we're looking. Instead of searching for the living, we're searching for the remnants of the dead. And in a galaxy that's 13 billion years old, where 99% of all the civilizations that have ever existed are probably already extinct, the dead vastly outnumber the living. Their radio signals have long since faded into the cosmic microwave background. Their light has been redshifted into invisibility. But their artifacts, their probes, their structures, their technology, could still be out there, silently drifting, waiting to be found. Oumuamua might be our first hint of this galactic graveyard. Our first glimpse of the monuments left behind by those who came before us. Now, let me talk about the skeptics, because I want to be fair to both sides of this debate. There are very smart people who think the artificial hypothesis is premature, and they make some good points. First, they argue that we've only seen one of these objects. Drawing conclusions from a sample size of one is always dangerous. Maybe Oumuamua is just a statistical fluke, a natural object that happens to have a very unusual combination of properties. Maybe the next 10 interstellar objects we find will all be clearly natural comets or asteroids, and Oumuamua will be revealed as an anomaly. Second, they point out that our models of interstellar chemistry and physics are still incomplete. Maybe there are natural processes we haven't thought of yet that can explain Oumuamua's behavior. Maybe there's some exotic form of ice that's stable in interstellar space and sublimates invisibly. Maybe there's some weird interaction between solar radiation and the object's surface that we don't understand. Science has a history of finding natural explanations for things that initially seemed impossible. Third, they worry about the social and professional consequences of being associated with the alien artifact hypothesis. Scientists who study UFOs or claim to have found evidence of extraterrestrial visitation often find their careers damaged, their credibility questioned, their funding cut. It's a third rail in science. Even if you're right, you might not survive long enough to be vindicated. So there's a strong institutional pressure to find natural explanations, even if they're awkward or require a lot of assumptions. I get all of these concerns. They're valid. Science is supposed to be conservative. We're supposed to be skeptical of extraordinary claims. We're supposed to prefer simple, natural explanations over complex, exotic ones. But, and this is important, conservatism can go too far. If we're so afraid of being wrong that we refuse to consider possibilities that make us uncomfortable, we're not being good scientists. We're being cowards. And here's what I think is the most important point in this whole debate: we don't have to settle this by arguing. We can actually find out. We can build the missions. We can intercept these objects. We can study them up close. We can gather the data that will definitively tell us whether they're natural or artificial. The question isn't whether we should speculate about Oumuamua. The question is whether we're going to do the work to find out the truth. And that brings me to what I think is the real legacy of Oumuamua, regardless of what it turns out to be. This object has fundamentally changed how we think about our solar system and our place in the galaxy. Before 2017, we could pretend that our solar system was isolated, that the space between stars was empty, that we were alone in our little bubble. Oumuamua shattered that illusion. It proved that objects from other star systems pass through our neighborhood. It proved that the galaxy is connected, that matter flows between the stars, that we are part of a larger ecosystem. We now know that we live in a cosmic highway, not an island. We're a rest stop on an interstellar road, and travelers pass through regularly. We just haven't been paying attention. That changes everything. It changes how we think about planetary formation, because material from other star systems can seed new planets. It changes how we think about the origin of life, because organic compounds or even microbes could potentially travel between stars inside these objects. It changes how we think about the future of humanity, because if we ever become a spacefaring civilization, we'll be adding our own artifacts to this galactic flow. Oumuamua also taught us humility. It reminded us that the universe is under no obligation to make sense to us. It doesn't care about our categories or our expectations. It's going to keep surprising us, keep challenging us, keep forcing us to expand our understanding. And that's good. That's how science is supposed to work. We should be uncomfortable sometimes. We should be confused. That's when we learn the most. There's something else I want to talk about, something that doesn't get discussed as much but is really important: the emotional impact of Oumuamua. For a lot of people, myself included, this discovery was deeply moving. There's something profound about knowing that an object from another star system passed through our neighborhood. Even if it's just a rock, it's a rock that has seen things we'll never see. It's traveled distances we can barely comprehend. It's a messenger from the deep cosmos, a piece of another world that briefly touched ours. And if it is artificial, if it is some kind of technology from another civilization, God, that's overwhelming. That's the kind of thing that makes you want to laugh and cry at the same time. Because it would mean we're not alone. It would mean that somewhere, someone else looked up at the stars and wondered. Someone else built tools and machines. Someone else tried to explore the cosmos. And even if they're gone now, even if we're separated by millions of years and light years of space, there's a connection there. A kinship. We're part of the same story. I think about the scientists who built Oumuamua, if it is artificial. I imagine them in their laboratories or their workshops, designing this probe, testing it, preparing it for launch. I imagine them standing on their world, maybe a planet, maybe a space station, maybe something we don't have words for, and watching it depart. I imagine them knowing that this object would outlive them, outlive their civilization, outlive their star. I imagine them sending it out anyway, driven by the same curiosity, the same need to explore, that drives us. And I think about us, standing here on Earth in 2017, with our primitive telescopes and our incomplete theories, trying to make sense of what we saw. Two civilizations, separated by unimaginable gulfs of space and time. Connected by a single tumbling object. It's beautiful. It's tragic. It's humbling. Even if I'm wrong, even if Oumuamua is completely natural, I can't shake the feeling that this was a momentous encounter. We saw something from out there. We observed it, we studied it, we tried to understand it. And for a brief moment, the isolation of Earth was broken. We were part of something larger. Now, let me address something that I know is on a lot of people's minds. Why didn't Oumuamua try to communicate with us? If it was a probe from an advanced civilization, wouldn't it send a signal? Wouldn't it try to make contact? Maybe. But maybe not. Think about our own space probes. We've sent spacecraft to every planet in the solar system, and many of them are still functioning, still collecting data. But they don't actively look for alien civilizations. They're not designed to. They have specific missions: study this planet, photograph that moon, measure these radiation levels. If an alien civilization happened to be on one of Jupiter's moons, our probes might fly right past without noticing, because they're not programmed to look for signs of intelligence. Oumuamua could be the same. If it's a probe, it might have a very specific mission that has nothing to do with finding life. Maybe it's mapping the distribution of heavy elements in the galaxy. Maybe it's studying stellar populations. Maybe it's looking for something we can't even imagine. Earth and its radio transmissions might be completely irrelevant to its purpose. Or maybe it did try to communicate, in a way we couldn't detect. We listen for radio signals, but what if it was transmitting in a different part of the electromagnetic spectrum? What if it was using neutrinos or gravitational waves or some form of communication we haven't discovered yet? We might have been standing right next to a shouting person, deaf to their voice because we were listening at the wrong frequency. Or, and this is the explanation I find most plausible, maybe it's just too old. If Oumuamua was launched millions or billions of years ago, any power systems it had would have failed long ago. Batteries die. Solar panels degrade. Even nuclear power sources eventually decay. A probe that old would be completely inert, a dead shell tumbling through space. It might have sensors and transmitters, but if there's no power, they're useless. We're looking at a ghost ship, a relic from a bygone age. This is the technofossil hypothesis, and I think it's the most likely scenario if Oumuamua is artificial. We're not looking at a functioning probe. We're looking at a corpse. A monument to ambitions that were pursued long before humans existed. And you know what? That's okay. Even a dead probe would be an incredible discovery. It would tell us about the material science of an alien civilization. We could study how it was constructed, what it's made of, how it's held together. We could learn from it. We could be inspired by it. Even in death, it could teach us about life in the universe. There's one more aspect of Oumuamua I want to discuss, and it's the question of its origin. Where did it come from? Which star system launched it? We don't know. We can't know. The problem is that stars move. Over the millions of years that Oumuamua has been traveling, all the stars in the galaxy have shifted positions. If we trace Oumuamua's path backward, it seems to come from the general direction of the constellation Lyra, near the bright star Vega. But Vega wasn't in that position when Oumuamua would have left its home system. The geometries don't line up. This means one of two things. Either Oumuamua comes from a star system that's so far away we can't identify it, or it's been traveling for so long that its origin is effectively untraceable. Both possibilities suggest an object of immense age, a wanderer that has been drifting through the galaxy for longer than we can easily comprehend. Think about that journey. Hundreds of millions of years, maybe more, traveling through absolute darkness. Passing through the outskirts of other star systems, maybe even passing close to other planets. Did it fly past alien worlds? Did any of those worlds have life? Did any of them have civilizations that noticed it and wondered about it, just as we're wondering now? We'll never know. But it's humbling to realize that we're probably not the first ones to see Oumuamua. We're just the latest in a long line of observers, separated by eons of time and vast reaches of space, all trying to understand the same mysterious object. And Oumuamua? It doesn't care. It's indifferent to our questions, our theories, our telescopes. It's just doing what it's always done, tumbling through the void, following the laws of physics, slowly making its way across the galaxy. It will eventually pass near other stars, maybe even enter other solar systems. And maybe, millions of years from now, another civilization will look up and see it. Another species will wonder what it is and where it came from. And like us, they'll find that the answers are just out of reach. This is the poetry of Oumuamua. It's a messenger, but the message is written in a language we can barely read. It's a visitor, but it doesn't stay for conversation. It's evidence of something, but we can't agree on what. It's simultaneously the most exciting and the most frustrating discovery in modern astronomy. Let me talk now about what happens next, because this story is far from over. Right now, as I'm speaking to you, Oumuamua is about 6 billion kilometers from Earth and getting farther every second. It's moving at about 26 kilometers per second relative to the Sun, which means it's putting about 2.2 billion kilometers between us every year. It's already far beyond the orbit of Neptune. It's approaching the heliopause, the boundary where the Sun's influence ends and true interstellar space begins. Soon, maybe it's already happened by the time you're reading this, Oumuamua will cross that boundary. It will leave our solar system forever. It will return to the state it's known for most of its existence, alone in the dark, frozen to temperatures just barely above absolute zero, silent and still except for its eternal tumble. It will rejoin the interstellar medium, that vast ocean of gas and dust and wandering objects between the stars. It will drift for another billion years, maybe more. It will pass through the local bubble, the region of low-density gas created by ancient supernovae. It will gradually climb out of the galactic plane, rising above or falling below the thin disk where most stars reside. It will continue its journey, indifferent to the passage of time, until perhaps it encounters another star system. And when it does, when it falls into the gravity well of another sun and swings through another system's inner planets, maybe someone will be there to see it. Maybe another civilization will point their telescopes at the sky and spot a fast-moving object on a hyperbolic trajectory. Maybe they'll debate what it is, just as we did. Maybe they'll launch their own Project Lyra to catch it and study it. Maybe they'll succeed where we failed. Or maybe not. Maybe Oumuamua will pass through system after system, unnoticed and unexamined, a ghost forever searching for witnesses who are never quite ready to see it. But while Oumuamua is gone, the search for interstellar objects is just beginning. The Vera C. Rubin Observatory, when it starts operations, will be an absolute game-changer. This telescope will be able to survey the entire visible sky every few nights, creating a constantly updated map of everything that moves. It's going to revolutionize asteroid detection, exoplanet discovery, and, most relevant for our purposes, interstellar object detection. Current estimates suggest that the Rubin Observatory will find somewhere between one and several interstellar objects per month. Think about that. Within a few years of operation, we might have a catalog of hundreds of these visitors. We'll be able to study their size distribution, their composition, their trajectories. We'll be able to see if Oumuamua was typical or anomalous. We'll be able to determine if the galaxy is full of weird needles with mysterious accelerations, or if Oumuamua was truly one of a kind. And that data will be invaluable. If every interstellar object we find looks like a normal comet or asteroid, then Oumuamua might just be a statistical outlier, a weird but natural object. But if we keep finding objects with extreme aspect ratios and non-gravitational accelerations, if we see a pattern, then the artificial hypothesis becomes much more compelling. Pattern is the enemy of the natural fluke explanation. There's also the possibility, remote but tantalizing, that we'll find an interstellar object that's clearly artificial. Imagine if Rubin finds an object that's perfectly spherical, or cubic, or shows obvious signs of manufacturing. Imagine if we detect radio transmissions or laser pulses coming from one of these visitors. Imagine if we find something that's actively controlled, that maneuvers in ways that can't be explained by natural forces. It could happen. And if it does, everything changes. But even if we never find a smoking gun, even if all future interstellar objects look natural, Oumuamua will have served an important purpose. It will have opened our eyes to the reality of interstellar traffic. It will have shown us that we need to pay attention to the space around us, that we can't just assume our solar system is isolated and unchanging. And it will have inspired us. It will have given us a mystery to solve, a challenge to overcome, a frontier to explore. It will have reminded us why we became scientists in the first place, because the universe is endlessly fascinating, endlessly surprising, and endlessly worth studying. I think about the graduate students who are working on Oumuamua research right now, poring over data, running simulations, writing papers. I think about the engineers designing the next generation of telescopes and spacecraft. I think about the kids in schools who are learning about this mysterious visitor and deciding they want to be astronomers when they grow up. Oumuamua has captured the public imagination in a way that most astronomical discoveries don't. People who never think about space are suddenly curious about interstellar objects and alien probes. News outlets that usually ignore astronomy are running stories about solar sails and Project Lyra. It's become part of our cultural conversation, part of how we think about our place in the universe. And that's important. Because ultimately, the question of whether we're alone in the universe is one of the most profound questions we can ask. It touches on philosophy, religion, identity, purpose. It shapes how we see ourselves and our future. If we're alone, and the universe is ours to explore and settle. If we're not alone, then we're part of a larger community, with all the opportunities and challenges that implies. Oumuamua doesn't answer that question definitively. But it makes it real. It makes it urgent. It transforms "Are we alone?" from an abstract philosophical question into a concrete scientific problem that we can actually investigate. And that's the real gift of Oumuamua. Not the data it provided, though that's valuable. Not the debates it sparked, though those are important. The real gift is the sense of possibility. The reminder that the universe is bigger and stranger than we imagine. The knowledge that we are surrounded by mysteries waiting to be solved. When I look up at the night sky now, I see it differently than I did before 2017. I see it as a busy highway rather than an empty void. I imagine all the objects that are passing through right now, too small or too dark for us to detect. I think about the fact that at this very moment, there might be a dozen Oumuamuas in our solar system, silent and invisible, carrying their secrets through our neighborhood. And I think about the future. About the day when we'll have telescopes powerful enough to spot these visitors regularly. About the missions we'll launch to study them. About the discoveries we'll make. About the questions we'll answer and the new questions we'll uncover. This is an exciting time to be alive. We're living through the transition from thinking of our solar system as isolated to understanding it as connected. We're developing the technology to detect and study interstellar visitors. We're beginning to grapple with the possibility that the galaxy might be full of artifacts from extinct or distant civilizations. We're at the threshold of a new era in astronomy. And Oumuamua was the herald of that era. The messenger that announced the change. The stranger that showed us we're not as alone as we thought. Let me tell you something that really blows my mind when I think about the physics of this whole situation. The acceleration that Oumuamua experienced was incredibly subtle. We're talking about a change in velocity of just a few meters per second over the course of weeks. To detect that, astronomers had to measure the object's position with incredible precision, then track how that position changed over time, accounting for the gravitational influences of the Sun, all the planets, even the larger asteroids. It's like trying to detect a feather's weight on a scale while an elephant is standing on the other side. But they did it. They detected that acceleration, and they couldn't explain it with gravity alone. The numbers didn't add up. And that's when the real detective work began. The thing about science is that it's not just about collecting data. It's about making sense of that data, fitting it into a coherent framework, testing hypotheses against observations. And when the observations don't fit any of your hypotheses, that's when things get interesting. That's when you know you're on the edge of something new. With Oumuamua, every hypothesis had problems. The Comet hypothesis failed because there was no outgassing. The hydrogen iceberg hypothesis failed because hydrogen ice shouldn't survive the journey. The nitrogen fragment hypothesis required an implausibly large population of similar objects. And the artificial hypothesis, well, that one was just too uncomfortable for most scientists to seriously consider. But here's the thing, discomfort doesn't make something false. Throughout history, scientific progress has often required us to accept ideas that initially seemed absurd. The Earth goes around the Sun. Absurd. Time slows down when you move fast. Ridiculous. The universe is expanding. Impossible. And yet, all of these turned out to be true, because the evidence demanded it. Maybe we're at one of those moments now. Maybe Oumuamua is demanding that we accept something that seems absurd, that we've been visited by technology from another civilization. Or maybe it's demanding that we invent new physics, new chemistry, new ways of thinking about how objects behave in the interstellar medium. Either way, we're being pushed beyond our comfort zone. And that's exactly where we need to be. Let me talk about the spectroscopy for a moment, because it's another piece of the puzzle that's really intriguing. When astronomers point a spectrograph at an object, they're essentially taking its chemical fingerprint. Different elements and molecules absorb and emit light at specific wavelengths, creating a pattern of dark and bright lines in the spectrum. It's like a barcode that tells you what something is made of. When they looked at Oumuamua's spectrum, they found nothing special. Just a flat, reddish continuum with no obvious features. No absorption lines from water ice or carbon dioxide or any of the usual suspects you'd expect on a comet. No emission lines that would indicate active processes on the surface. Just red. Now, you might think that's boring, but it's actually really weird. Even the most boring asteroids show some spectral features. You can usually identify at least some minerals in the surface. But Oumuamua, it was like looking at a blank wall. A perfectly smooth, featureless surface. If it's natural, that suggests the surface has been processed in some unusual way. Maybe it's been bombarded by cosmic rays for so long that all the volatile materials have been driven off, leaving behind only a residue of complex organic molecules. Those tholins I mentioned earlier would create exactly this kind of featureless red spectrum. But if it's artificial, that smoothness might be intentional. A manufactured surface, designed for some specific purpose, might not show the same kind of spectral features as a natural rock. Maybe it's a coating, a protective layer designed to shield the underlying structure from radiation and micrometeorite impacts. Maybe it's camouflage, making the object look natural to casual observers. We can't know for sure. But it's another data point, another piece of the puzzle that doesn't quite fit the normal pattern. You know what really gets me thinking? The timing of all this. Oumuamua arrived in our solar system just a few years after we developed the technology to detect such objects. The Pan-STARRS telescope that found it only came online in 2010. Before that, we simply didn't have the capability to spot something this small and fast-moving. So for all of human history, objects like Oumuamua could have been passing through our solar system, and we would have been completely oblivious. How many have we missed? Dozens? Hundreds? Thousands? And here's the really mind-bending part. If these objects are passing through regularly, and if some of them are artificial, then we've been under observation for who knows how long. Maybe for as long as we've existed as a species. Maybe longer. Think about that. Right now, as you're reading this, there might be a dozen interstellar objects in our solar system. Most of them would be too small to detect, dark little things no bigger than a car or a bus, drifting through the outer reaches of the solar system. If any of them are equipped with sensors, they might be watching us right now. Recording our radio transmissions, our television broadcasts, our satellite communications. Building a picture of Earth and its civilization. And we'd have no idea. We'd be completely unaware that we're being studied. Is that paranoid? Maybe. But it's also possible. And possibility is what science is all about. Let me tell you about another aspect of this that fascinates me, the rotation. Oumuamua was tumbling end over end with a period of about 8 hours. That's fast, but not impossibly so. What's interesting is that the rotation was stable. It wasn't wobbling or precessing in complicated ways like you'd expect from an irregular chunk of rock. It was tumbling like a well-balanced object. If Oumuamua is a solid piece of rock or metal, that stability makes sense. The object has a well-defined moment of inertia, and it's spinning around one of its principal axes. Simple physics. But if it's a thin shell or a sail, that stability is more interesting. A flexible structure would tend to vibrate or flutter as it rotates, especially after millions of years of micrometeorite impacts. The fact that Oumuamua maintained a stable tumble suggests either that it's very rigid, or that it has some kind of internal structure that keeps it stable. Maybe there are ribs or spars inside, like the skeleton of an umbrella. Maybe there's a dense core that acts as a stabilizing mass. Maybe the entire thing is made of some incredibly stiff material that doesn't flex even when it's thin. Or maybe it's just a rock, and I'm reading too much into this. The thing about mysteries is that they invite speculation. They make you think about possibilities you'd never consider otherwise. And whether or not those possibilities turn out to be true, the act of thinking about them expands your mind. It makes you realize how much you don't know, how many assumptions you make without even realizing it. Oumuamua has done that for me. It's made me question my assumptions about what's possible, what's natural, what's likely. It's made me realize that the universe might be far stranger and far more interesting than I ever imagined. And that's a gift, even if we never figure out what Oumuamua really was. Let me talk about the mathematics of interstellar travel, because it's relevant here. To get an object from one star system to another, you need to give it enough velocity to overcome the sun's gravity and enter interstellar space. For something launching from Earth's orbit, that's about 42 kilometers per second, the solar system escape velocity. Oumuamua was moving at about 26 kilometers per second relative to the sun when we first detected it. That's fast, but it's actually slower than the escape velocity. How can that be? The answer is that Oumuamua wasn't trying to escape our solar system. It was already in interstellar space when it arrived. Its velocity relative to the Sun is actually its velocity relative to the local standard of rest, plus the Sun's motion relative to that reference frame. When you do the math, it all works out. But here's what's interesting. 26 kilometers per second is relatively slow for an interstellar object. If Oumuamua had been kicked out of its home system by a gravitational interaction, say, a close encounter with a gas giant, you'd expect it to be moving faster. Ejection events tend to impart pretty high velocities. The fact that Oumuamua is moving relatively slowly suggests either that it's been traveling for a very long time and has lost some of its initial velocity through drag in the interstellar medium, or that it wasn't ejected violently but rather drifted out gently from its origin. Become the many worlds interpretation. His advisor, John Wheeler, admired the work but was troubled by its implications. Wheeler eventually distanced himself from it. The physics community was largely dismissive. Everett left academia, took a defense industry job, and never published seriously on physics again. He died in 1982 at the age of 51. Never knowing that his ideas would be taken seriously, let alone that they would eventually become one of the leading interpretations of quantum mechanics. His daughter later said he had believed he would live to see the vindication of his theory. He did not. Alan Guth was 32 when he stayed late in the lab on the night of December 6, 1979, and worked out the implications of what he called the inflationary scenario. He wrote in his notebook that it was a spectacular realization. The word spectacular was underlined twice. The inflationary model Guth developed has since been refined and modified by others, including Andre Linde, who developed what is called chaotic inflation, the framework most naturally suited to producing an eternal multiverse. Linde still works today, still passionate about ideas he has spent 4 decades developing. Max Tegmark has been described as the most openly enthusiastic advocate of the multiverse in contemporary physics. He holds a position at MIT. He gives public lectures. He writes books for general audiences. He is genuinely, visibly delighted by the ideas he works with, and that delight, for anyone who encounters it, is contagious. These are not mystics or dreamers. They are rigorous mathematicians who began with concrete physical problems and found, at the end of their equations, something they had not expected and could not deny. Much of what we know about the early universe, about inflation, about the conditions that gave rise to everything we see, we have learned from a faint whisper of radiation that fills the entire sky. The cosmic microwave background, or CMB, is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into hydrogen atoms, allowing photons to travel freely for the first time. Before that moment, the universe was opaque, a dense plasma through which light could not pass. After that moment, the universe became transparent, and the light that was released then has been traveling ever since. We detect it today as a faint microwave radiation coming from every direction in the sky, at a temperature of approximately 2.7 degrees above absolute zero. The CMB is remarkably uniform, but not perfectly so. There are tiny fluctuations, variations in temperature of about 1 part in 100,000, that map the distribution of matter in the early universe. Those fluctuations are the seeds from which all the large-scale structure of the cosmos, all the galaxies and galaxy clusters we see today, eventually grew. The pattern of those fluctuations is a direct consequence of quantum mechanics in the early universe. The tiny quantum fluctuations in the inflatant field were stretched to cosmic scales by inflation, imprinting a specific statistical pattern on the CMB. That pattern, described by what physicists call the power spectrum, is one of the most precisely measured quantities in all of science. And it matches, with extraordinary accuracy, the predictions of inflationary cosmology. This is significant. It means that the quantum fluctuations of the inflationary period, the same process that, according to the eternal inflation picture, continuously generates new bubble universes, are real and have real, measurable consequences in our universe. The Planck satellite, launched by the European Space Agency in 2009, measured the CMB with unprecedented precision. Its data confirmed the inflationary picture in remarkable detail and provided no evidence against it. Future missions, ground-based telescopes, next-generation space observatories, will continue to refine our picture of the CMB, looking for any anomalies that might hint at something beyond the standard inflationary model. Some researchers have claimed to see hints in the CMB data of exactly the kind of collision signature that would be expected if our bubble universe had, at some point in its history, grazed another bubble. These claims remain controversial. Other researchers, examining the same data, do not find compelling evidence for such a collision. The question is genuinely open. In 1998, two independent teams of astronomers made a discovery that changed our understanding of the universe's destiny. They had been studying a particular type of exploding star, a type Ia supernova, which produces a predictable amount of light, making it possible to use as a standard candle to measure cosmic distances. By comparing how bright these supernovae appeared to how bright they were expected to be at various distances, the teams were mapping the rate at which the universe had been expanding over its history. The expectation was that gravity, the mutual attraction of all the matter in the universe, would be slowly decelerating the expansion over time. The universe was born in the hot, explosive Big Bang, but gravity should, over billions of years, be putting the brakes on. Perhaps eventually halting the expansion. Perhaps even reversing it, leading to what cosmologists call the Big Crunch, a final catastrophic recollapse. Instead, the supernovae told a different story. The universe is not slowing down. It is speeding up. The expansion of the universe is accelerating. Distant galaxies are moving away from us not more slowly with time, but more quickly. Something is pushing outward. Something is overcoming the gravitational pull of all the matter in the universe and driving the cosmic expansion to accelerate. That something was given a name, dark energy. And its nature remains one of the deepest unsolved problems in all of physics. The leading candidate is the cosmological constant, the energy of empty space. Even empty space, it appears, is not truly empty. It has an intrinsic energy density, a kind of baseline pressure, that drives expansion. That energy density is extraordinarily small, a tiny positive value rather than the enormous positive or negative value that most theoretical predictions would suggest. But it is there. And it dominates the universe's destiny. If dark energy continues to drive accelerating expansion, and current observations suggest it will, then the universe faces a slow, cold, lonely end. Over hundreds of billions of years, galaxies will drift farther and farther apart. Stars will exhaust their fuel and go dark. Eventually, even black holes will evaporate, leaving a universe of almost perfect emptiness, expanding forever toward a maximum entropy, a cosmic stillness so profound it is almost peaceful. This is the fate of our bubble universe. But in the eternal inflation picture, it is just one story in a library of stories that never ends. Other bubbles are being born even as ours ages and cools, Other universes are beginning their stories. The vast, inflating substrate continues, indifferent to the quiet endings of the bubbles it has produced. There is one aspect of the multiverse that most physicists prefer not to dwell on for too long, because it leads very quickly into territory where physics shades into philosophy and philosophy shades into something altogether stranger. The question of consciousness. In the many worlds interpretation, every time a quantum event occurs, the universe branches. The branches are all real. The beings in each branch are all real. But each being, each version of you, in each branch, experiences only one outcome. Each version of you has a continuous subjective experience, a sense of being a specific person in a specific world, even though from the outside there is no collapse, no selection, no fact of the matter about which branch is the real one. How does this work? How does a subjective, acceleration, the local standard of rest, and I can't shake the feeling that we're looking at something made rather than something born. But you know what? It's okay not to know. It's okay to be uncertain. That's the human condition, especially when we're pushing the boundaries of knowledge. We don't always get clear answers. Sometimes we get mysteries, and we have to live with them. What I do know is this: Oumuamua changed us. It expanded our perspective. It forced us to consider possibilities we've been ignoring. It reminded us that the universe doesn't owe us easy answers or comfortable truths. And it inspired us to keep looking, keep searching, keep trying to understand. That's the real legacy of the needle in the dark. Not what it was, but what it made us become. As I finish writing this, Oumuamua is about 7 billion kilometers away, in the darkness beyond Neptune, continuing its endless journey. It's indifferent to our questions. It doesn't know we exist, or if it does, it doesn't care. It's just following its trajectory, obeying the laws of physics, tumbling through the void like it has for millions of years. But we care. We noticed. We wondered. We tried to understand. And even though it's gone now, even though we may never know for sure what it was, the act of trying matters. The questions we asked, the debates we had, the missions we designed, all of that matters. Because that's what makes us human. That's what separates us from rocks and trees and bacteria. We're the species that looks up at the sky and asks why and what if and could it be. Oumuamua gave us a gift. It gave us a mystery worthy of our intelligence, a puzzle worthy of our creativity, a challenge worthy of our ambition. And whether it was a rock or a machine, whether it came from a dead planet or a living civilization, it served its purpose. It made us look up. It made us wonder. It made us realize that we are part of something much, much larger than ourselves. And that realization, that moment of cosmic perspective, is worth everything. The needle is gone now, back in the dark where it came from. But we remain, standing on our small blue planet, pointing our telescopes at the sky, waiting for the next visitor. And when it comes, and it will come, we'll be ready. We'll have better instruments. We'll have faster spacecraft. We'll have more data, more theories, more experience. We'll be prepared in ways we weren't in 2017. But most importantly, we'll have the knowledge that Oumuamua gave us, that we are not isolated. That we are part of a galaxy-wide ecosystem of matter and energy and motion. That objects from other star systems do visit our neighborhood. That the space between stars is not empty, but is instead a busy highway of wanderers and messengers and ghosts. We live in an age of wonders. We live in a time when the impossible becomes possible, when the distant becomes close, when the unknown becomes known. We live in an era when a strange object can visit from another star system, and we can actually detect it, study it, and begin to understand it. What a time to be alive. What a privilege to witness this. What an honor to be part of the generation that first encountered Oumuamua and began to grapple with what it means. The story of Oumuamua is not just about an object. It's about us. It's about our curiosity, our intelligence, our determination to understand the universe we inhabit. It's about our place in the cosmos and our role in the grand story of existence. And that story is just beginning. Look up tonight. Look at the stars. And remember, between those points of light, in the vast darkness of interstellar space, objects are moving. Some are rocks. Some might be machines. Some carry the signatures of worlds we'll never see, of civilizations we'll never meet, of stories we'll never fully know. But they're there. They're real. And sometimes, just sometimes, they pass close enough for us to see them. Oumuamua was one of those times. And there will be more. The universe is vast and ancient and full of mysteries. But we're here. We're watching. We're ready. And when the next messenger arrives from the deep, we'll be waiting with our telescopes and our spacecraft and our insatiable curiosity. Because that's what we do. That's who we are. We're the ones who ask questions. We're the ones who seek answers. We're the ones who refuse to accept ignorance when knowledge is possible. We're humanity. And we've just encountered our first confirmed visitor from another star system. This is just the beginning of a much longer, much stranger story. And I, for one, can't wait to see what happens next. The mathematics of detection. Let me dive deeper into something that really showcases human ingenuity, how we even managed to detect Oumuamua in the first place. This isn't like spotting a plane in the sky or even a satellite orbiting Earth. We're talking about finding a relatively small object, maybe a few hundred meters long, that's millions of kilometers away and moving at tens of kilometers per second. It's like trying to spot a grain of sand on a beach from a mile away, except the grain is moving and the beach is three-dimensional space. The Pan-STARRS telescope that discovered Oumuamua is specifically designed for this kind of work. It takes repeated images of the same patch of sky, then compares them to look for anything that's moved. Most of the stars stay in the same place because they're so far away that their motion is imperceptible over short timescales. But closer objects, asteroids, comets, satellites, show up as moving dots. The challenge is distinguishing real objects from artifacts. Cosmic rays hit the detector and create false signals. Satellite trails and airplane contrails contaminate the images. Even birds flying past the telescope can create confusing signals. The software has to sort through all of this noise to find the genuine astronomical objects. When Oumuamua first appeared, it looked like just another dot. The software flagged it as a potential asteroid and added it to the list of objects to follow up on. But when astronomers looked at its trajectory more carefully, they realized something was off. The orbit didn't close. It wasn't bound to the sun. It was passing through. That's when people got excited. That's when they realized they were looking at something truly special. Think about the precision required to measure Oumuamua's trajectory. You need to know its position to within a few hundred kilometers, and it's tens of millions of kilometers away. You need to measure how fast it's moving to within meters per second, and it's traveling at 26 kilometers per second. The math is brutal, but astronomers are good at this. They've been tracking objects in the solar system for centuries, refining their techniques, improving their instruments. They can measure the position of a spacecraft near Jupiter to within centimeters. They can predict where a comet will be decades in advance. They're masters of celestial mechanics. With Oumuamua, they used every trick in the book. They observed it from multiple locations around the world to get parallax measurements. They tracked it over several weeks to build up a detailed picture of its trajectory. They accounted for the gravitational influences of all the major planets, the pressure of sunlight, even the relativistic effects predicted by Einstein's theory of general relativity. And that's how they detected the anomaly. The acceleration. The tiny deviation from a purely gravitational trajectory. It was small. Really small. If you were riding on Oumuamua, you wouldn't feel anything. But over weeks and months, that tiny acceleration added up. The object was deviating from where it should be if gravity was the only force acting on it. And that deviation couldn't be explained by any known natural process. The psychology of scientific discovery. There's a psychological dimension to this whole story that I find fascinating. How do scientists react when they encounter something that doesn't fit their models? How do they deal with uncertainty and ambiguity? Different people react in different ways. Some get excited. They see anomalies as opportunities, chances to discover something new. These are the people who thrive on uncertainty, who are energized by mysteries. They're usually the ones pushing for unconventional explanations, willing to take risks and challenge the established paradigm. Others get defensive. They've spent their careers building models and theories, and they don't want to see those models overturned. They'll work hard to find conventional explanations, to fit the new data into the existing framework. They're not being dishonest. They genuinely believe that the simplest explanation is usually the right one, and the simplest explanation is one that doesn't require new physics or alien civilizations. Still others get frustrated. They want clear answers, definitive conclusions. Ambiguity makes them uncomfortable. They might even avoid working on problems like Oumuamua because the uncertainty is too much to deal with. All of these reactions are human and understandable. Science is often portrayed as this perfectly rational enterprise where people follow the data wherever it leads, but in reality, it's messier than that. Scientists have egos, biases, career concerns. They have favorite theories and pet peeves. They have emotional investments in their ideas. The key is recognizing these biases and trying to compensate for them. Good scientists are self-aware. They know they have biases, so they try to be extra careful. They seek out contradictory evidence. They invite criticism. They change their minds when the data demands it. With Oumuamua, I think we're seeing both the best and worst of scientific culture. The best, people are genuinely trying to figure out what this thing is, using all the tools and techniques at their disposal. They're proposing hypotheses, testing them, refining them. They're having robust debates about interpretation and methodology. The worst, there's a lot of tribalism. People are lining up into camps based on whether they think it's natural or artificial, and sometimes they're being dismissive or even hostile toward the other side. There's concern about professional reputation, about not being seen as a crackpot. There's conservatism that sometimes tips over into dogmatism. But overall, the process is working. We're making progress. We're gathering data, refining our models, moving toward a better understanding. It's messy and contentious and sometimes frustrating, but that's how science works. That's how we inch toward truth. The cultural impact. Oumuamua has had an impact far beyond the scientific community. It's captured the public imagination in a way that most astronomical discoveries don't. Part of that is the name. Oumuamua just sounds cool. It's exotic and memorable in a way that 1I/2017 U1 could never be. It evokes the idea of a scout or messenger, which immediately suggests a narrative, a story. Part of it is the mystery. People love mysteries. They love puzzles that don't have easy answers. And Oumuamua is one hell of a puzzle. Is it a rock? Is it a machine? Where did it come from? Why is it shaped like that? Why did it accelerate? These questions don't have definitive answers yet, and that's part of the appeal. Everyone can speculate. Everyone can have an opinion. It's not like some discoveries where the experts tell you what something is and that's the end of it. With Oumuamua, even the experts are debating. I've seen Oumuamua referenced in novels, TV shows, documentaries, podcasts. It's become part of popular culture, a symbol of the unknown, the mysterious, the potentially alien. That's powerful. That's the kind of thing that inspires people, that makes them think about the bigger questions. And I think that's important. In a world that can feel small and mundane, where everything seems to be known and cataloged and explained, Oumuamua reminds us that there's still mystery out there. There are still questions without answers. There are still frontiers to explore. That matters for kids especially. I think about young people learning about Oumuamua in school, seeing that scientists don't have all the answers, that there are real mysteries being investigated right now. Some of those kids are going to become scientists because of this. They're going to decide they want to be part of solving these puzzles. And even the ones who don't become scientists will carry something with them. A sense of wonder. A sense that the universe is bigger and stranger than it appears. A sense that we're part of something larger. That's the real cultural impact of Oumuamua. Not what it is, but what it represents. Mystery. Wonder. Possibility. The engineering challenge. Let's talk about what it would take to actually build something like Oumuamua, if it is artificial. Because I think that's an interesting thought experiment, and it helps us appreciate what we might be looking at. First, the materials. If Oumuamua is a solar sail, it needs to be incredibly thin and incredibly light, but also incredibly strong. It has to withstand the forces of acceleration, the impacts of micrometeorites, the thermal stresses of passing close to a star. And it has to do all of this for millions of years. We don't have materials like that. Not yet. The thinnest solar sails we've built are about 25 microns thick, about a quarter the thickness of a human hair. And they're only designed to work for a few years at most. To build something that could last for millions of years, you'd need materials that are far more advanced than anything we currently have. Maybe graphene. Maybe carbon nanotubes. Maybe some metamaterial that can self-repair when damaged. Maybe something we haven't even thought of yet. But let's say you've solved the materials problem. You've invented some super strong, super thin material that can survive the interstellar medium. Now you need to build the structure. How do you manufacture something that's hundreds of meters across but only microns thick? You probably can't do it on a planetary surface. Gravity would tear it apart. You'd need to build it in space, maybe in orbit around a low-gravity moon or asteroid. You'd need sophisticated manufacturing techniques, probably involving robots or nanomachines that can work in vacuum. And you'd need quality control. Every flaw in the structure is a potential failure point. A single crack could propagate and tear the whole thing apart. So you'd need to inspect every square meter, fix every defect, ensure that the entire structure meets your specifications. That's hard. Really hard. It would require an enormous investment of resources and technology. But it's not impossible. It's the kind of thing a sufficiently advanced civilization could do. And if they could do it, they probably would. Because a solar sail is such an elegant solution to interstellar travel. It doesn't require fuel. It doesn't require engines that break down. You just unfurl it and let starlight push you wherever you want to go. It's slow, sure. It would take thousands or millions of years to cross the distance between stars. But if you're not in a hurry, if you're thinking in terms of deep time, that's okay. You send out your sails and you wait. Eventually, they reach their destinations. And maybe they don't even need to be crewed. Maybe they're just autonomous sensors, collecting data, sending it back home via laser or radio. Or maybe they don't send anything back. Maybe they just record, storing the data for some future retrieval that may never come. The point is, building something like Oumuamua is hard but not impossible. It's within the realm of what an advanced civilization could do. And that makes the artificial hypothesis at least plausible. The statistics of interstellar objects. Let me talk numbers for a moment. How common are interstellar objects? How often should we expect to see them? Before Oumuamua, we didn't know. We had theoretical models that predicted maybe a few interstellar objects should pass through the inner solar system every century. But models are just guesses. We needed actual observations. Now we have one data point. We've seen one interstellar object in the few years since Pan-STARRS came online. From that, we can extrapolate. If we've seen one in a few years of monitoring, there are probably dozens or hundreds or even thousands of interstellar objects passing through the solar system all the time. Most of them are too small or too dark for us to detect, but they're there. When the Vera Rubin Observatory starts operating, we'll get a much better census. We'll find fainter objects, smaller objects, more distant objects. Within a few years, we should have dozens or even hundreds of confirmed interstellar visitors. And that's when the statistics will start to tell us something. Right now, we can't say much based on a sample size of one. But with dozens or hundreds, we can start to see patterns. We can measure the size distribution, the velocity distribution, the composition distribution. We can see if Oumuamua is typical or unusual. And if we find more objects with similar characteristics, extreme shapes, non-gravitational accelerations, positions near the local standard of rest, then we'll have to take the artificial hypothesis much more seriously. Because one weird object could be a fluke. But a population of weird objects? That's a pattern. And patterns demand explanations. Of course, it could go the other way. Maybe all the other interstellar objects will be obviously natural. Maybe they'll be round, inactive, moving in ways that make perfect sense. Maybe Oumuamua will be revealed as a unique oddball, interesting but not representative. Either way, we'll learn something. We'll refine our understanding of what's out there, what's normal, what's anomalous. That's the power of statistics. One measurement tells you almost nothing. 100 measurements start to reveal the underlying distribution. And from that distribution, you can infer the processes that created it. I'm really excited about the next few years. I think we're going to see some amazing discoveries. And even if none of them are as weird as Oumuamua, we're going to learn a lot about the interstellar medium, about planetary formation in other star systems, about the dynamics of ejection and capture. This is just the beginning of interstellar object astronomy. We're pioneers, exploring a new field, learning as we go. And that's an incredible privilege. The philosophical implications. Let me get philosophical for a moment. What does Oumuamua mean for our understanding of our place in the universe? For most of human history, we thought Earth was the center of everything. The sun and moon and planets revolved around us. We were special, unique, central. Then Copernicus showed that Earth orbits the sun. Then we realized the sun is just one star among billions in our galaxy. Then we realized our galaxy is just one among billions in the observable universe. Each discovery pushed us further from the center, made us less special. This is sometimes called the Copernican principle. We're not special. We're not central. We're just typical inhabitants of a typical planet orbiting a typical star in a typical galaxy. Oumuamua adds another layer to this. It shows that our solar system isn't isolated. We're not separate from the rest of the galaxy. Objects pass through. Matter flows in and out. We're connected to the larger galactic ecosystem. And if Oumuamua is artificial, that connection is even deeper. It would mean other civilizations have been here, at least in the sense that their technology has visited our neighborhood. We're not alone in our exploration of space. We're latecomers to a very old, very crowded galaxy. That's humbling. It puts our achievements in perspective. We're proud of our space program, our missions to the Moon and Mars and the outer planets. But if Oumuamua is artificial, it means someone else mastered interstellar travel long before we even existed as a species. At the same time, it's inspiring. It means it's possible. If someone else did it, we can too. We can build our own interstellar probes, send them to other star systems, explore the galaxy. And maybe, millions of years from now, one of our probes will pass through some distant solar system. Maybe the inhabitants will spot it with their telescopes. Maybe they'll debate what it is, just as we're debating Oumuamua. Maybe they'll wonder about the civilization that built it, whether we're still out there somewhere, what became of us. That's the long view. That's thinking in terms of deep time, geological timescales, the rise and fall of civilizations and species and even stars. It changes how you think about things. Suddenly, our political squabbles seem petty. Our national borders seem arbitrary. Our conflicts seem pointless. We're all humans, on one small planet, orbiting one typical star, in one typical galaxy. And we're surrounded by a universe that is vast and ancient and largely indifferent to our existence. That's both terrifying and liberating. Terrifying because it makes us feel small and insignificant. Liberating because it means our problems aren't as important as they seem. The universe doesn't care about our stock markets or our elections or our wars. It's going to keep on going whether we survive or not. But we can care. We can choose to care. We can choose to work together, to explore, to understand, to survive. And maybe that's the real message of Oumuamua. Not that we're being visited by aliens, but that we're part of something larger. That we need to think beyond our immediate concerns and consider our place in the cosmic story. That we need to grow up, as a species, and start thinking like citizens of the galaxy rather than isolated inhabitants of a single planet. The future of humanity. This brings me to something I've been thinking about a lot, what Oumuamua means for the future of humanity. Right now, we're still confined to one planet. We've sent a few people to the moon, we have a space station in low Earth orbit, we have robots exploring Mars. But we're still fundamentally an Earth-based species. If something happened to Earth, an asteroid impact, a nuclear war, a climate catastrophe, we'd be extinct. That's a precarious position to be in. It's like keeping all your eggs in one basket. If the basket drops, you lose everything. The long-term survival of humanity requires that we spread out. We need to colonize other worlds, establish self-sufficient settlements that can survive independent of Earth. We need to become a multi-planet species. And eventually, if we last long enough, we need to become an interstellar species. We need to send missions to other star systems, establish colonies around other suns, spread throughout the galaxy. It sounds like science fiction, but it's actually a practical necessity if we want to survive for millions of years. The sun won't last forever. In a few billion years, it will expand into a red giant and swallow the Earth. If we're still around, we'll need to be somewhere else. Oumuamua gives us a glimpse of what that future might look like. If it's artificial, it's an example of technology that has survived for millions of years, crossing the vast distances between stars. It's proof that interstellar travel is possible, that civilizations can spread beyond their home systems. And even if it's natural, it's still valuable. It's a sample of material from another star system. By studying it, we can learn about planetary formation elsewhere in the galaxy. We can see what's out there, what resources might be available, what challenges we'll face. This is practical knowledge. If we're going to send missions to other star systems, we need to know what we're getting into. We need to understand the interstellar medium, the types of objects we might encounter, the hazards we'll face. Oumuamua is teaching us these lessons. It's showing us that interstellar space is not empty, that it's full of objects both natural and possibly artificial. It's teaching us to be vigilant, to watch the skies, to be prepared for the unexpected. And it's inspiring us. It's showing us that the galaxy is accessible, that interstellar travel is not just a fantasy but a real possibility. That's important. Because the future of humanity depends on our ability to dream big, to think beyond our current limitations, to imagine possibilities that seem impossible. Oumuamua is one of those possibilities made real. It came from out there. And someday, we'll go out there too. The ethics of contact. Let me talk about something that makes a lot of people uncomfortable. What should we do if we definitively confirm that Oumuamua or another interstellar object is artificial? This is a question that has been debated in the SETI community for decades. If we detect a signal from an extraterrestrial civilization, should we respond? And if so, what should we say? With Oumuamua, the situation is a bit different. It's not sending us a message. It's not trying to communicate. It's just passing through. So the question isn't whether to respond, but whether to pursue. Should we launch a mission to intercept it? Should we try to capture it or bring back samples? Should we try to study it up close, potentially disturbing or damaging it in the process? These are difficult ethical questions. On one hand, the scientific value of studying an alien artifact would be immense. It would be the discovery of the millennium. We'd learn things we can't even imagine right now. On the other hand, if Oumuamua is artificial, it belongs to someone else. Even if that someone is long gone, even if they'll never know what we did with their property, there's still a question of respect. Should we interfere with an object that isn't ours? And what if there's some risk involved? What if Oumuamua is carrying microbes or nanomachines or something we don't understand? What if studying it unleashes something dangerous? These are not just academic questions. They're practical considerations that would need to be addressed before launching any mission. My personal view is that we should study it if we can. The potential benefits outweigh the risks. We'd be careful, of course. We'd take precautions. But we shouldn't let fear or excessive caution prevent us from investigating what might be the most important discovery in human history. Others disagree. They argue that we should leave it alone, that we have no right to interfere with objects from other civilizations, that the risks are too great. I respect those views, but I don't share them. I think the pursuit of knowledge is one of the highest human values. I think we have a responsibility to learn as much as we can about the universe we inhabit. And I think that responsibility extends to studying interstellar objects, even if they might be artificial. But I also think we need to be thoughtful about how we do it. We need to have international agreements about who decides, who benefits, how the information is shared. This isn't something that one country or one organization should control. This is a question for all of humanity. And we need to be prepared for the consequences. If we confirm that we found alien technology, it will change everything. It will change how we see ourselves, how we organize our societies, how we think about our future. We need to be ready for that. The search continues. So where do we go from here? What happens next in the saga of Oumuamua and interstellar objects? First, we keep watching. The Vera Rubin Observatory will come online soon, and it will revolutionize our ability to detect these visitors. We'll build up a catalog of interstellar objects, study their properties, look for patterns. Second, we plan missions. Project Lyra is already in development, but it needs funding and political support. We need to convince governments and space agencies that this is worth doing, that intercepting an interstellar object should be a priority. Third, we prepare our minds. We need to be ready for whatever we find. Whether it's strange rocks or ancient machines, we need to approach it with open minds and careful reasoning. And fourth, we keep debating. We keep arguing about what Oumuamua is, what it means, what we should do about it. Because that debate is healthy. It's how we refine our ideas, challenge our assumptions, move toward truth. The story of Oumuamua is not over. It's just beginning. We're in the first chapter of what might be a very long book. And how that book ends depends on us, on the choices we make, on how we respond to this mystery. I'm hopeful. I think humanity is up to this challenge. I think we can figure out what Oumuamua is. I think we can build the missions to study it and other interstellar visitors. I think we can handle the truth, whatever it turns out to be. But I'm also patient. I know that science takes time. I know that some questions don't have quick answers. I know that we might not get closure in my lifetime. And that's okay. Because the pursuit is its own reward. The questions are as valuable as the answers. The journey is as important as the destination. Oumuamua has given us a journey to embark on. A mystery to solve. A frontier to explore. And that's a gift worth cherishing. So here's to Oumuamua, wherever it is now, whatever it is. May it continue its journey through the stars. May it visit other worlds and inspire other civilizations. May it serve as a reminder that the universe is vast and strange and full of wonders. And may we be worthy of the mystery it has given us. The story continues. The search goes on. And we remain, looking up at the stars, wondering what else is out there, waiting to be found. What a time to be alive. What a privilege to witness this moment in history. What an honor to be part of the generation that first encountered Oumuamua and began to grapple with what it means. The needle in the dark has passed through our lives. But its impact will last forever. It has changed us, challenged us, inspired us. And for that, I am grateful. Thank you, Oumuamua. Thank you for visiting. Thank you for the questions. Thank you for the wonder. Safe travels, messenger. May your journey never end. May you find what you're seeking, or may those who seek find you. Until we meet again, in some distant future, when our own probes tumble through the cosmic dark, carrying our own messages to civilizations we'll never meet. Until then, we'll keep watching the skies. We'll keep asking questions. We'll keep searching for truth. Because that's what we do. That's who we are. We're humanity. And we've just met our first visitor from the stars. The adventure is only beginning. The technical details that matter. Let me get into some of the technical details that really make this story fascinating, because the devil is in the details, and those details are what separate informed speculation from wild guessing. When we talk about Oumuamua's non-gravitational acceleration, we need to be precise about what that means. Astronomers measured its position at multiple times and calculated its trajectory. If gravity was the only force acting on it, the trajectory would follow a perfect hyperbola, a specific mathematical curve determined by Newton's and Einstein's equations. But Oumuamua's actual trajectory deviated from that perfect hyperbola. Not by much. We're talking about deviations of maybe a few 100,000 kilometers over the course of months. But that's enough to be statistically significant. The measurements were precise enough that these deviations were well outside the margin of error. To quantify this, astronomers use something called the A2 parameter, which measures the magnitude of the non-gravitational force. For Oumuamua, A2 was about 4.9 times 10 to the power of -60/day-2. That's a tiny number. It means the acceleration was about 0.00001 meters per second squared. For comparison, Earth's gravity at the surface is about 10 meters per second squared, 1,000,000 times stronger. But tiny as it was real and measurable. And it couldn't be explained by any known gravitational effects. So something else was pushing on Oumuamua. The question is what? And that's where all the theories come in. If it was outgassing like a normal comet, the force would come from gas jets escaping from the surface. The gas carries momentum, and by Newton's third law, that creates a reaction force that pushes the comet in the opposite direction. It's rocket propulsion on a tiny scale. For Oumuamua, if outgassing was responsible for the acceleration, you could calculate how much gas would need to be escaping. The numbers depend on what kind of gas you assume, water vapor, carbon monoxide, whatever, but in general, you'd need to lose somewhere between a few kilograms and a few tons per second. That might not sound like much, but over the months that Oumuamua was under observation, it would add up to between tens of thousands and millions of kilograms of material. And all of that should have been visible to our telescopes. We should have seen dust reflecting sunlight. We should have detected gas absorbing or emitting specific wavelengths. We should have seen something. We didn't. The upper limits on dust and gas production from all the observations we made were orders of magnitude below what would be needed to explain the acceleration. It wasn't just that we didn't see outgassing. It's that we can definitively say there wasn't enough outgassing to account for the motion. That's what makes this so puzzling. The data rules out the obvious explanation. So then you start looking at less obvious explanations. Could the outgassing be invisible? That's where hydrogen and nitrogen come in. These are gases that don't produce much visible signature, so you might not see them even if they were there. But both of these have their own problems. Hydrogen ice shouldn't survive the interstellar journey. Nitrogen ice requires an implausibly large population of similar objects. Neither explanation is satisfying, which leaves solar radiation pressure. And the thing about radiation pressure is that it's well understood. We know exactly how much force sunlight exerts on an object. It depends on the object's cross-sectional area, its reflectivity, and its distance from the sun. Given Oumuamua's distance and brightness, we can calculate what its mass would need to be for radiation pressure to produce the observed acceleration. And the answer is very low mass relative to its size. So low that the object would need to be incredibly thin or incredibly fluffy. And given that it held together during its passage close to the sun, fluffy seems unlikely. Which leaves thin. How thin? The calculations suggest maybe a millimeter or less. For an object that's hundreds of meters across, that's insanely thin. That's not a rock. That's a sheet. A membrane. A sail. And that's where the artificial hypothesis comes from. Not from wild speculation, but from careful mathematical analysis of the observations. Could the analysis be wrong? Sure. Maybe there's some effect we haven't accounted for. Maybe the mass estimates are off. Maybe there's some exotic physics at play. But based on what we know, based on the laws of physics as we understand them, the simplest explanation for all the observations is that Oumuamua is a very thin object being pushed by sunlight. And we don't know of any natural process that creates such objects. The importance of remaining skeptical. Having said all that, I want to emphasize the importance of skepticism. It's easy to get caught up in the excitement of the artificial hypothesis and start seeing aliens everywhere. But that's not good science. Good science requires skepticism. It requires that we constantly question our assumptions, check our calculations, look for alternative explanations. It requires that we don't jump to conclusions just because they're exciting. So let me play devil's advocate for a moment and present the strongest case against the artificial hypothesis. First, we've only seen one interstellar object. Drawing firm conclusions from a sample size of 1 is always dangerous. Maybe Oumuamua is just a statistical fluke, a 1 in a billion combination of properties that happens to look artificial but is actually natural. Second, we don't fully understand all the processes that can occur in the interstellar medium. Maybe there are forms of ice or types of molecular structures that we haven't thought of yet. Maybe there are chemical reactions or physical processes that can create thin, rigid objects naturally. Third, the artificial hypothesis requires that alien civilizations exist, that they've developed interstellar travel, and that their artifacts are common enough that we'd find one in just a few years of looking. Those are all big assumptions. Each one individually is plausible, but together, they might be less likely than we think. Fourth, if Oumuamua is artificial, why haven't we found others? If the galaxy is littered with alien artifacts, we should be tripping over them. The fact that we've only found one suggests that either they're extremely rare, or Oumuamua is not actually artificial. These are all valid points. They're reasons to be cautious about accepting the artificial hypothesis. They're why most scientists remain skeptical. But they're not reasons to dismiss the possibility entirely. They're reasons to keep looking, keep studying, keep gathering data. They're reasons to be careful, not to give up. And that's the position I think we should take. We should be skeptical of the artificial hypothesis, but not dismissive. We should recognize that it's one possibility among several, probably not the most likely, but still worth considering. And we should let the data decide. As we find more interstellar objects, as we study them in more detail, as we refine our models and theories, the truth will eventually emerge. Until then, we wait. We watch. We wonder. And we remain appropriately skeptical, while staying open to possibilities that might challenge everything we think we know. The lesson for future discoveries. I think Oumuamua teaches us an important lesson about how to approach future discoveries. Because this won't be the last time we encounter something weird in space. The universe is full of surprises, and as our instruments get better, we're going to find more and more things that don't fit our expectations. How should we respond? I think we should respond with curiosity tempered by caution. We should be excited about anomalies, because that's where new knowledge comes from. But we should also be careful not to jump to conclusions. We should propose multiple hypotheses and test them rigorously. We should look for the simplest explanation that fits all the data, but we shouldn't be afraid to consider more exotic possibilities if the simple explanations fail. We should communicate our findings clearly and honestly, acknowledging uncertainty where it exists. We should avoid overhyping results, but also avoid being so cautious that we miss important discoveries. And most importantly, we should remain open-minded. Science progresses by challenging accepted wisdom, by being willing to admit when our models are wrong, by following the evidence wherever it leads. Oumuamua is a test case for all of this. It's teaching us how to deal with ambiguity, how to balance skepticism with open-mindedness, how to have productive debates about controversial interpretations. These lessons will serve us well in the future. Because the next Oumuamua might not be ambiguous. It might be clearly artificial. And when that day comes, if it comes, we'll need to be ready. We'll need to have protocols in place for studying it. We'll need to have international agreements about who makes decisions and how information is shared. We'll need to have thought through the implications and prepared ourselves mentally and emotionally. Oumuamua is giving us a chance to practice. It's a dress rehearsal for first contact, in a sense. It's showing us where our gaps are, what we need to improve, how we need to prepare. And that's valuable, regardless of what Oumuamua actually turns out to be. The final word. As I bring this long exploration to a close, I find myself coming back to the central question: what was Oumuamua? And the honest answer is, I don't know. Nobody does. We have hypotheses, we have theories, we have passionate arguments on all sides. But we don't have certainty. Maybe it was a chunk of nitrogen ice from a distant Pluto-like world. Maybe it was a hydrogen iceberg, however implausible that seems. Maybe it was some exotic form of matter we haven't thought of yet. Or maybe, just maybe, it was something made by someone. A tool. A probe. A sail. A monument. We may never know for sure. Oumuamua is gone, racing back into the interstellar void, and catching up to it gets harder every day. Even if we launch Project Lyra tomorrow, there's no guarantee we'll reach it in time or learn what we need to know. But that's okay. Because the not knowing is part of the beauty. The mystery is part of the wonder. Oumuamua came from somewhere we can barely imagine, traveled distances we can hardly comprehend, survived conditions that would destroy anything we've ever built. It passed through our solar system for a few brief weeks, showing us just enough to make us curious, just enough to make us wonder, but not enough to give us answers. And then it left. Back to the dark. Back to the cold. Back to the endless journey through the galaxy. But it left us changed. It showed us that we're not isolated. It reminded us that the universe is full of mysteries. It challenged us to think bigger, to wonder more, to question our assumptions. That's the legacy of Oumuamua. Not the data it provided, not the papers it spawned, not even the debates it created. The real legacy is the sense of wonder it instilled. The reminder that we're part of something larger. The knowledge that out there, in the dark, things are moving. Things we don't understand. Things that might change everything if we could just get a closer look. And maybe we will. Maybe the next interstellar visitor will be easier to study. Maybe it will answer the questions that Oumuamua raised. Maybe it will raise new questions we haven't even thought of yet. Either way, we'll be watching. Because that's what we do. That's who we are. We're the species that looks up at the sky and asks why. We're the ones who wonder what's out there. We're the ones who refuse to accept ignorance when knowledge might be possible. Oumuamua was our first confirmed visitor from another star system. Our first messenger from the deep. Our first glimpse of the interstellar travelers that passed through our neighborhood. It won't be the last. The story continues. The mystery deepens. The search goes on. And somewhere out there, tumbling through the darkness between the stars, a needle-shaped object continues its journey. Indifferent to our questions. Unmoved by our theories. Silent as it has been for millions of years. But we saw it. We noticed it. We wondered about it. And in doing so, we took our first real step into the larger galactic community. Welcome to the interstellar age, humanity. Welcome to a universe that is stranger, older, and more crowded than we ever dared imagine. The adventure has only just begun.